Hey you, it's me. Today we're going to talk about stacks. Oh, oh,
That was weird.
I'm sure we've all been in this situation before. You're the first person on the elevator. You press your floor. Then people start to come into the elevator after you. Looking at the backs of everyone's heads, you realize you're going to have to wait for all of them to exit the elevator before you're able to. While that might be a simple and specific scenario, that's pretty much how stacks work. The first item pushed into the stack will be the last item removed from the stack. So in other words, the last item in is the first item out. That's why we call stacks LIFO, last in, first out, data structures. But what's so cool about stacks? Well, I bet you interact with a stack every single day without even realizing it. The undo functionality that comes in most applications is a stack, and so is our browser history. We look and the last thing we did is at the very top. And the further down the stack we go, the older the operations are. And we use stacks in everyday programming languages a lot more than you might think as well. We can take, for example, our call stack. When one function calls another function, they form what is called a stack of function calls. Your CPU keeps track of the memory location of the functions in a stack-like manner, so it knows who the caller was when the current function is done executing. And secondly, they're just really useful when it comes to trees and graphs. Whether we use our own implementation of them or just rely on our call stack with recursion. And last but not least, they make for great interview questions. I'm sure some of you are already thinking about the implementation details of a stack. If you were thinking of using an array, then you're right. If you were thinking of using a linked list, then you're also right. Stacks are what we call abstract data structures. They don't have just a single implementation. As long as whatever data structure you use has the expected interface and the time and space complexities required by your task, you've got a stack. So today we're going to cover the array and linked list implementations of a stack. Quick side note, today we're going to use the same linked list definitions from our previous video. So if you haven't seen my video on how to build a linked list from scratch, check it out. Before we get our hands dirty with implementation, let's define our stack interface. The first method a stack offers is called push. Push inserts an element to the top of the stack. Usually, a push into an array-based stack should cost us O1 amortized time and O1 space. Amortization utilizes a time complexity accounting method that is far beyond the scope of today's video. But here's the general rule of thumb. If for every n-1 independent O1 operation, you had to do a single ON operation, then in most cases we can say that ON operation gets amortized, which is just a fancy way of saying it gets averaged out to be O1 when you include it with all the n-1 single O1 operations. So in our case, if we had to resize the array with the cost of ON time, for every n-1 O1 push operations, our ON push operation would cost us O1 amortized time. And lastly, when we describe amortization in our time complexities, we say that the best case scenario would be O1 time, the average case scenario would be O1 time, and the worst case scenario would be ON time. Okay, let's move on to our second method, pop. Pop removes the top element in our stack. This should cost us O1 amortized time, only this time it'll be in reverse. If we were to shrink our underlying array every time its occupied space fell below n over 2, where n is the length of the array, then we would have to copy roughly n over 2 elements every n over 2 times. Our third method is called peek. Peek returns the value of the element at the top of the stack without removing it. This will cost us O1. And our final method will be isEmpty. IsEmpty will tell us if our stack contains any elements. And like peek, isEmpty will cost us O1 time. Alright, we've defined all the essential methods for a stack, so let's start building. First, we're going to cover an array-based stack. Almost all modern languages offer array implementations that allow us to use arrays as stacks through their built-in methods without having to define anything on our own. So for example, we'll get this started by creating a stack using an empty array. And something to note here, our method to insert new elements to the top of our stack we called push. But through our array implementation in Python, we will utilize the append method. It's going to do the same thing, it just has a different name. After we append 1 to our previously empty stack, let's print it out and see what happens. So we see here, we have a stack with only one element, 1. Let's add another element with the value of 2 to our stack. As you can see here, an array-based stack actually pushes elements to the far right of the array. Next, let's see our pop method in action. Thankfully, Python implemented it under the same name. And it simply just removes the last element from the array. Instead of defining an isEmpty method, let's just utilize the functionality that it would be implementing. If the length of the stack is 0, then it's true, it's an empty stack. If it's not 0, then false, it's not empty. And lastly, we can peek into our stack by simply accessing the element at index -1. This will always give us the last element in the array without ever knowing exactly how many indices there are. If we needed to use a stack during an interview, this would be a sufficient implementation. However, for the sake of thoroughness, let's build a stack that doesn't rely on predefined array methods or a self-resizing array. Since our stack is still based on an array, but we're no longer relying on Python to resize the array for us, our stack class constructor will take in a size parameter. We'll use that size to initialize our underlying array. The next thing we do is initialize an index variable. This index will point us to the last element that was inserted into the stack. We'll initialize it to -1 to start to represent the fact that there's nothing in our stack. Every time we want to push a new element into our stack, we'll increase our index variable by 1 and then store that new element at that location. And this is a little Python specific, but this is where we define how we want our stack to be serialized. That way we get an expected outcome when we try to print it, instead of just memory addresses. The first method that we'll implement is the easiest one, isEmpty. IsEmpty returns true if our index equals -1, or in other words, there's nothing in our stack yet. Double simply doubles the size of our array every time we run out of space. We're implementing this because we said we wanted a wholesome implementation that did not rely on Python to resize our underlying array. But if the language you're using does automatically resize an array, it's completely up to you whether or not you want to implement this method. And our double method will actually return without doing anything if we haven't fully occupied our array's available space yet. But we see here when our array has now been fully occupied, we take its current length, multiply that by 2, and now redefine the size of our array. Let's implement our push method. The first method push will always call is double. Remember that double will actually exit early if the array has not reached its maximum capacity. That's why it's totally okay to call double on every single push operation. Once double is finished, we first increment our index. In the case that we're pushing in the first element in the stack, our index will go from -1 to 0, giving us the first index in the array. Because remember, arrays are 0 indexed. And lastly, we just assign the given value to the appropriate index. Pop should start out with half, which does the opposite of what double does. It halves the array if we're using less than half the space. I left out its implementation because it's fairly straightforward, especially if you've already built the double method. It's just working in the opposite way, where instead of doubling the length, you're just halving the length. The first thing our pop method will do is check, is the list empty? If the list is empty, we have no items to pop. We could potentially throw an error here, but since error handling is really language specific, I've opted to just return none. If the list isn't empty, then we enter into our if statement. First, we'll store the element that we have at self.index into a temporary variable. Then we remove that element from our array by reassigning the value at the index to none. We'll decrement our index variable by 1, moving it one element to the left, and we return the element that we stored in our temporary variable. Last but not least is peek. Peek only returns the element at the top of our stack. It doesn't remove or alter anything. But before we can return the top element of our stack, we need to make sure that we actually have elements in the stack. We'll call isEmpty. If isEmpty is false, then self.index is where the most recently added element sits. We can go ahead and just return that value. Otherwise, we'll just return none. Now that we've written all that, let's test it out a little bit. Make sure everything comes out the way that we're expecting. We see here, we initialize our stack with size 2. That's how big we're saying our underlying array should be when we first start our stack. We can push elements 1 and 2 into our stack without having to resize anything. Now, when we push 3 and 4, our stack will actually have to resize. Even though we know it's not empty, let's just double check and see what happens. Is our stack empty? False. After that, we can take a little peek at what our top element would be, and it'll be the last element that we pushed into the stack. Now, if we call pop for every element in our stack, we should have removed all the elements, right? Let's see what our stack looks like. And let's try isEmpty one more time. Array-based stacks are fairly easy to implement. The concept revolves around how we manage an array, so we read, write, and remove everything from a single side. Perhaps the trickiest bit would be the double method. But all we're really doing there is swapping out an array that is too small for an array twice the size. And surprisingly enough, this doesn't affect our average time complexity, which is 0.1. Okay, so that was a lot, but you should be impressed with yourself if you've made it this far. The next stack implementation will be a linked list based stack. And as mentioned before, I grabbed my implementation from my linked data structures video. Go check it out if you haven't already. Or if you have your own implementation of a linked list, feel free to use that. The first thing I'll do here is define a class called linked stack. And once again, we'll create our string helper method. This will make sure that we're printing out our linked list in a human readable format. Next, let's just take a second to think about how we actually want to implement this linked list as a stack. In our array example, we pushed and popped everything to the very end of the list. This allowed us to do all of our operations in O1 time. If we did it at the front of the array, it would actually cost us ON because of the constant resizing and shifting we would have to do. But remember, linked lists actually have the opposite cost. Inserting or removing from the front will cost us O1 versus at the very end, which would cost us ON. So let's just take advantage of that and organize our data in the opposite way of how we just did it in the previous example. Let's start with our isEmpty method. For that, we can utilize a length method on our linked list. However, the length method of a linked list actually would cost ON because you'll have to traverse through the entire chain to find out how many nodes there are. That's not great. We could potentially optimize this by adding a length property to our class. Then all we have to do is increment or decrement our length every time we add or remove a node from our linked list. There is a trade-off for adding our own length property versus just recounting the length every time. That trade-off comes in the form of just adding more complexity. So while it sounds great right now, the more properties you include, the more complex your code grows and the harder it is to maintain. But I think that this is like a classic software engineering conundrum, right? You'll have two options, they both have their pros and cons. It's up to you as the developer to evaluate what's the best way to go about it. You can make an argument for both ways. The next method we'll implement is push. As you may recall, the insert and pop methods from our linked list append and remove from the top of the list, so we can just use those methods. Notice that the cost associated with swapping arrays is no longer included in this implementation. There's no extra space allocation needed as we're not working with a sequential data structure. So next is our pop, and we can totally take advantage of the pop method of our linked list, which just removes the head of the linked list, if one exists, that is. And last but not least is peek. We could simply check if we have a head node, and if we do, just return that value. And the other way to do this is to actually access our linked list head property directly. This will cost us O1. I hope that seeing how stacks, an abstract data structure, can be constructed in different ways made the concept more approachable for you. I think it's really cool to see how sequential and non-sequential data structures can be used to create the same end product, albeit with some minor differences in time complexities. That, to me, is one of the most rewarding but intimidating parts of software development. There's hardly ever an exact right way to do something. Many times you'll have several different ways of implementation, but it all comes down to how you evaluate your trade-offs. In this case, the overall time complexity and complexity in our code could be the deciding factor for the underlying data structure. And as always, if there's any algorithm, pattern, or problem on LeetCode that you want to go over, let me know in the comments. And from me to you, have a great day. And as mentioned before, I grabbed my implementation from my link data structure. From my link. If you recall, a pen. Cool. Amortized. Right? Amortized.
Amortize.